welcome to one of the last Grey Scott Thursday, because Grey Scott Thursdays was a series of webinars we've organized every Thursday at 10, starting in January and ending next week. So this one today is feedback on the GTC, who will be presented by Pierre Aubert himself. Pierre is part of the organization team. He's a research engineer from the LAPP, a French laboratory of physics and particles in Annecy, in the French mountains ever. And there is Karim, Azum, and I from Terratech within the French NCC called CCFR, and with the LAPP of Annecy, we co-organize the Grey Scott Thursdays and the Grey Scott School. So those Grey Scott Thursdays you discovered were held by 9 incredible teachers who gave you webinars on their topics, introducing at the same time the program of the summer school. What is Grey Scott School? It's a free summer school dedicated on programming and optimization on heterogeneous architecture. It was created 2 years ago by Pierre, with a few people in Annecy, and the French NCC joined him last year to help him develop it not only in Annecy, but also in 12 satellite sites among 4 countries. Those satellite sites helped us reach more people by broadcasting the school live in their locations. And the summer school had a 2-week program, 1 week on CPU and 1 on GPU, and everybody was free to choose the courses they wanted to attend, thanks to our a la carte option. Last year, we finally trained over 500 people. Everything is available still on replays on our website and YouTube channel. You can access it if you want, but everything is in French. This year, obviously, we're going European, so everything will be in English, like this webinar. You have various ways to attend the school, and you'll see in the video I'm going to launch for you that now it's time to register. Spots in Annecy are full, but you can participate online or in one of our satellite sites. We have various satellite sites in France, in Germany, in Luxembourg, in Slovenia, in Belgium, in Senegal, and in Netherlands. And especially in France, you can choose between Paris, Marseille, Nantes, Reims, Rouen, and Toulouse. Everything is free, but registration is mandatory. So now it's time to register. Don't wait for it. And let me now play for you the video who will present you the school that will start in less than 2 weeks now.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grey Scott School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or a la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Sycl, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, CuPy, CU Numeric, JAX libraries and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G Fortran and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Nsight, Malt and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
So if you have any question regarding the school, if you wish to register, you can ask them in the Q&A section. Pierre and I will be glad to answer you. Thank you for listening to me. Now it's time to give the floor to Pierre.
So hello everybody, thanks for being at this webinar. So today we will talk about little feedback on the GTC 2025. So GTC stands for GPU Technical Conference, with the conference of NVIDIA about new hardware, new software improvement in hardware, software, etc. So it is the technical part of this conference. And so today we will mainly talk about GTC. So the GTC is really big. So this year we had something like 1231 talks, so it's a lot. So of course I will not summarize all of them, just few. We'll start with a small detour by CES about rendering and stuff like this, and then we will see hardware evolution, library, tools evolution, feedback, and the new roadmap, because of course we are in 2025, so there is a new roadmap of NVIDIA presented by Jensen here on the stage. So first, let's start with a small detour by CES. So with Blackwell RTX. So Blackwell RTX, it's a GPU for rendering. So the same, we have Ada Lovelace for to render. So it's an open architecture, but for the rendering. So with no computing in float 64, for example, but much more on float 32, because it's mainly used for the precision okay for rendering. So Blackwell RTX, we have a bunch of stuff in Blackwell RTX. So first we have 92 billion transistors, so a lot. GDDR7 memory, 173 processor, so 21,000 cores, so it's a lot. Fourth generation of RT core, so ray tracing core, we'll see that in a minute. 4 peta operation of AI, so 3 times one of Ada Lovelace. 380 ray tracing teraflops, also much more. 125 shader teraflops. 1.8 terabyte per second on memory bandwidth. Shadow execution rendering, so as I presented that I think 2 years ago, something like that. So the idea is to reorder the shader during the rendering to improve the efficiency of the computation. So we'll see that also a bit. AI management processor, and I never talk about that, but this time I had it only cost $549, not $1,500 as Ada Lovelace, so the third of the price. And it consumed the half compared to Ada Lovelace with the same quality of the result on the output rate, so with less computation, with a lot of streak, and we will see that also, even if the hardware is better, but there is a lot of trick involved in it, and we will see that also together now. So first I have to define what is a rendering pipeline. So first we will talk about shaders. So basically once you have render a scene like this, for example, you will have a lot of materials. So for example, woods, you will have glass, rocks, or even lights, and they are all shaders. And basically, if you want, a shader will tell how to render a pixel, which color, something. Of course, it's a bit more complex than this, but just to keep that in mind, a shader is linked to a pixel. And shader reordering can improve the performance, especially if you have texture or stuff like that. Because, for example, a shader can have a texture, for example, a wood texture. If you reorder all the shader which are using the same wood texture together, they will use the same resources, and everything will be faster because everything is already in the memory. So it is one example of many, but this is the idea. So how do we do ray tracing? First, because RT core, ray tracing core are for ray tracing, and Ada Lovelace was also for ray tracing, and Blackwell RTX is also for ray tracing. So if I have a scene like this, I put a camera on it, and let's say, okay, I want to render this pixel here, this one. So what can I do? So the ray tracing method, or the physically accurate method, because we can call that also this way, consists to say, okay, the pixel should see a part of the scene. Which one? This one. So we trace a path, a line here, until we hit something. And here we want to check what is the material here. And here we will hit some glass, some metal, some stuff like this. So we will have some reflection, refraction, diffusion, lots of stuff in it. And once we take account this kind of stuff, then we will bounce, for example, on the book here. And after the book, maybe we will have another diffusion on a source light. And then we integrate the path and say, okay, the source light emit light on this book, and the book emit light, reflect light on this surface, and then we have refraction, and then we get the pixel here, and we sum all the contribution to get the value of the pixel here. This is very costly. The good point is we can do all of this in parallel for all the pixels, because all the pixels are independent in this case, so it's nice, but it's still a lot of computation. And it's really a lot of computation. So, and once we did a rendering for one scene like this, we have to do it for each frame. So if we have some movement, some changing in whatever, so we have to redo a rendering with all the ray tracings of all the pixels. That could cost really a lot. And the number of bounces also, you can increase the number of bounces to increase the accuracy of the rendering. The more you add bounces of the rays, and the more you will have accurate images, but the more it consumes resources to render. So how to speed up ray tracing? So first, let's imagine we want to render a model. Ray tracing is basically a lot of intersection computation. So basically, you have a ray, and you want to say, okay, do I cross a triangle or not? And to do that, imagine you have a model to render. Of course, you don't want to try to ray trace one ray with all the polygons of this model, especially if it's a heavy model. You can have thousand or million of polygons inside the model. So you don't want to check every single polygon in it, because some are hidden, some are not, some are completely away of your array, so you don't want to be bothered with that. So the trick is to do BVH, so a bounding volume hierarchy, so a kind of a tree if you want, to separate physically the triangle and know where they are. So you have your array, you check if you intersect a box, and then you will search inside the children of the box, and etc., until you get some triangles. Of course, you don't want to have only one triangle per box, it will be too costly. So you check you try to have only a cluster of some triangles inside the box. But that's the idea. And so to speed up that, in Blackwell RTX, there is a box intersection engine. So the hardware is capable to tell you if you have an intersection on a box. There is a triangle cluster compression engine also. So once you have a bunch of triangles you want to compress this cluster, you can, by hardware also. A triangle cluster intersection engine. So once you iterate inside your BVH and you get the good point, the good part of your BVH, you can ask the hardware, do I have an intersection inside this cluster of triangle? Then we deal also with opacity micromap engine. So the idea to that is to deal with transparency of shader, because for example you can have typically foliages, and then for foliage you will have normally a really simple geometry, maybe one or two triangles, not more, and you will trick the shape of your foliage with just the shader, and you put transparency above it and just the contour of the leaf you want to have, or the foliage in general. And this is quite costly, because the problem with transparency, if once you have transparency inside the shader, you have potentially to take account what's behind it. And so it's a bit tricky to do, but this part can do it well also for intersection, so there is no problem with the hardware again. And the last one is the linear swept spheres. So the idea is to deal with hair and fur rendering. So for example, you have hair is a curve, so it's really thin, it's really long, and you want to be able to know if there is an intersection with the ray you trace from your camera. So again, this is quite tricky, and the hardware is capable to do that. So with a lot of geometry, so mega geometries, there is some trick also. They are available in Vulkan with clusters and P-class, and in Optics 9.0, so it's quite okay. Of course, just the surface of the problem, because there is a lot of stuff involved in Blackwell RTX. So if you want to know more, I invite you to read the NVIDIA RTX Blackwell GPU architectures. It's really interesting. It's 51 pages. It's really interesting, and if you want to learn about that, it's really well done. Oh, it's not the end yet. This is for the technical part, but we do some ray tracing efficiently, but we do not have a render yet. So we have a pipeline for rendering, and the classic rendering pipeline, as we can use for ADA, for example, consists to that. We have a scene before, and we render one frame of the scene with ray tracing in 4K, for example. We have 4K images, and then we do that several times to have a full video sequence, and that's it. So we have to ray trace all the pixels for all the frames each time in 4K. It's a lot costly. For Blackwell RTX, it's not the same stuff, even if the hardware, as I said before, is more powerful than the hardware of ADA. There is other tricks involved in it. So the first one is to say, okay, let's render in 720p instead of 4K with ray tracing. So it costs a lot because it's ray tracing, but much less because you have only in 720p and not in 4K. Then we oversample from 720p to 4K with a neural network for that. So train just to add details where you want to have details. And it's not finished yet, because once you have a frame, you have another model which is capable to extrapolate the next 3 frames of your model. So to summarize, you render 1 pixels. In 1 pixel, you determine 16 of them, and with the 16 of them, you determine 64, or you have 64 of them at the end. So it's a lot of tricks to do that. But it's not the end yet, because we have new materials also. So as I said before, classically a material is a shader. So here you have a really simple shader. It's a fragment shader. So basically a shader will deal with the color of what you want to render. You can have for meshes, for whatever you want. You have plenty of shader. And then you have some inputs. So it's a really simple language, as Adrien mentioned in his webinar. It's really simple. It's really mathematics, because of course, once you do some rendering, it's mathematics under the hood. So here you have input as normal, so the normal of the surface that you want to render, the color, the view, so the point of view of the camera, the light, if you have some lighting, the direction of the light, and the output of the color you want to have in your pixel. So it's really simple. Of course, you can have much more complex shader, but this one is really simple. The one from the example of Vulkan, I have to mention. And then with that, you can have this kind of materials. Of course, it's not everything. You should have a texture or other stuff to do that, but with that, you can render material. And what they did in Blackwell is to say, okay, it's nice to have a shader, but it's quite costly. You can have some texture, you can have extra information. It could be really heavy to use. So they train a model to mimic all the shader, most of the shader possible. So with 64 neurons for all layers, and from 5 to 10 layers. So it's a really, really small neural network, but it works to mimic the material that we can have in a rendering scene, in a scene normally that we want to render. So it's nice also to have that in mind. So let's have a look to the demonstration. So first we render in a really small image. So this is the resolution of the image inside the slide. And then we oversample it into with the standard material into the size that we want. So potentially 4K, but of course my slides are not in 4K, so I cannot show you that. And then we have another rendering with neural materials. So you oversample, and instead of using a low resolution rendering with classical material, you use the neural material instead, and then you have extra details, extra details in your material. You can play the game of the 7 differences. You will normally spot much more than 7 differences because it adds detail where you should not have some details. But it's quite it's really interesting at the end to have this kind of stuff. So that's for the Blackwell RTX demo. And to say a bit, not too much inside the rendering, a little word about Vulkan and tensor cores. Because as Adrien said before in his presentation on Rust and Vulkan, there is a problem because you can do Vulkan, you can use Vulkan to do some graphics, some rendering pipeline, a lot of stuff. It's really powerful, it's really efficient. And the other way, you can do some computing with tensor core. And you cannot mix them together, and it's a pity. Not anymore. Now you can use cooperative vectors inside your shader to call the tensor core, and the GPU will understand that you want to use the tensor core of your GPU. So now it's possible to do that. So normally Adrien should be happy with this news. I hope, hopefully, and you should be happy too. So a little word on CUDA now. CUDA new features. We have some updates, so we'll stay in the computing, in the software right now. So we have CUDA.core. For Python programming, so imagine you have a compute.py script and you want to execute it maybe on the CPU with Python, maybe on a GPU as a kernel, and you can define it with a C++ a user-defined kernel or a Python-defined kernel, as you want. And if you run it on the CPU, you will have the Python interpreter, classically, it's normal. And on the GPU, now you can use NVRTC, so the NVIDIA real-time compiler, because now it can understand Python and create the kernel that you want to use with the proper argument in it. And you have a CUDA core launch to launch the kernel with all the information in it to be sure that everything is fine. So that's one use for CUDA core. Then we have CUDA parallel and CUDA cooperative. So the idea is to have a parallel computing but in a more Pythonic way, because of course once you use CuPy or PyCUDA or stuff like that, it's basically a wrap of the C++ library inside Python, but it's not Pythonic, it's a C++ way of doing things. And for Python developer, it could be not really natural. So here they rewrite the top, the interface on the top of the C++ library to be more Pythonic and more friendly for people who want to develop in Python in a more natural way for the compared to the Python way of doing things. So, and it's more also easy to integrate them into existing Python code. You don't have to rethink everything, so normally should be quite okay, and you can scale efficiently with that. We have some news from Nsight also, because Nsight now is capable to support the Python call stack, which was not really the case last year. It was a bit the case, but not too much. Now it's really the case. So no problem anymore. And to stay in Nsight, we have NVTX. So last year I presented to you NVTX. So NVTX is the way to add some extra panel inside Nsight to say to the profiler, okay, I mean in this function I'm doing that and that and that. So you give hint in the track of Nsight. So when you want to have a look to all the trace, all the information, you can say, okay, I was doing this kind of stuff with a call of everyone here, and you can manage everything. So it was okay for C++ and Fortran now, but now it's also okay for Python and Rust. So if you want to do some NVTX for Python or for Rust, you can. It's possible, it's working, no problem. Let's talk about Nickel now. So NVIDIA Collective Communication Library, so we'll talk about a lot of communication. So the goal of Nickel is to be able to do communication at every kind of scale. So the simple server scale, so we have 8 GPU, for example, on a server, or you have a DGX with 8 GPU also, but an NV switch, so you have to take advantages of the NV switch also. And maybe you have a GB200 NVL72, so with 72 GPUs in it, and you want also to take advantages of everything, and Nickel is capable to do that. And you want maybe to scale up inside a computing center, and it's also possible. And Nickel, to do that, will express 4 kinds of parallelism. So the really first one, the simple one, is data parallelism. So it's generally used for deep learning, but of course it's a strategy, so you can use it for everything you want, but it's mainly done for deep learning. So the idea is to say you have a model, and you are lucky, your model fit into your GPU, so it's fine. You can say, I have a bunch of data, I'll pass the data through the GPU, I compute my error, I compute my gradient, and update my weights, and everything is fine, no problem. If you have more data, you can say, okay, but it's a bit tricky. Let's put the model into 2 GPUs and split the data into 2 and pass all the data to the 2 GPUs. So we have local gradients, and then we have to do a Nickel all reduce to gather all the gradient to be sure that everything is consistent. At this point, Nickel is capable to use the NV switch to perform the reduce, because the switch, since 2022, they can do the reduction and all the reduction and all the message duplication by themselves. You don't have to rely on the GPU for that. it's not a good idea. Let the switch do that. It's here for that. And then once the reduce is done, you propagate the global gradient, and everyone has a global gradient that you can update all the weight properly, so no problem. And the problem is, if you increase the number of GPU, you want to increase the batch size, and you can have some trouble with the accuracy because you have a big batch size. So it's always a trade-off. You have to play a bit with that to be sure that everything is fine. Then we have layer parallelism, so you are less lucky. You have a bigger model, and the model does not fit inside your GPU. But you can say, okay, let's put the first part into one GPU, the second into a second GPU, and the third into the last GPU. Okay. And then you pass your data through the first, the second, and the third. You compute the error, you compute the gradient you want to update, and you do that in the reverse to upgrade your full model. So it's also possible to do that this way. You can also say, okay, I have a much bigger problem to treat. So I can fit one tensor inside the GPU, but not much. So one tensor per GPU for a really big model. And then you pass your data through this network of GPU, and then you get your error, your backpropagation, and etc., etc., etc. The problem with that is you need a lot of communication, and really efficient communication if you want to train faster this kind of model. And sometimes you may need specific hardware for that. We will see that at the close to the end of the presentation. Not totally, but close to the end of the presentation. The last level of parallelism we have is the expert parallelism. So the idea is to have a model, and the model will choose which expert to ask the question to. And then the expert and the model will have some errors. They will compute their gradient, their weight update, and they will propagate to the other model to make sure that everything is coherent, and that's it. And of course, Sycl is capable to combine all these 4 different ways of parallelism together. So with rings, basically. So I did a full presentation on that, I think it was 2 years ago, 1 or 2 years ago, maybe 2. So if you want to have a look, you can get the link. I can put the link if you want. But we have some news now on Sycl. So first we have from 5 to 20% improvement in terms of training. And then we have a parallel tree algorithm, some RAS subsystem to diagnose the application, so we can debug now in Sycl, which is quite a good point. We have profiler plugin in Sycl, and a new stack will come in few months. So that's why I asked a question last week about that in the GPU Python webinar. And the 2.27 will have symmetric memory allocation and latency divided by 4. So you have 4 times less latency than before. And this is due to the symmetric memory directly. This is an idea which comes at first from NVHMEM, which it was inspired by NVHMEM. And the point is to say, if you have a complex topology to deal with a lot of GPUs, if you do an allocation, you do the same allocation on every GPU, so you don't have to check each time you go on a GPU if the allocation is okay, if your data is okay. And this saves a lot of time, and this comes from the factor of 4 of the latency improvement. So because they are both in NVIDIA, so they talk to each other, and they were inspired by NVHMEM for that. The version 2.28 will have custom operation, computation, and communication fusion, and new algorithms. So I don't have some details with that, but normally should come in at least normally next year. There will be an integration with a high-level device, so MLAyer or TileAir. I will see that at the end of the presentation also. Now you will be able to build algorithms in Python and compile them on the fly with CUDA. So you will be able to do that. Not yet, but you will be able to do that at some point. And the integration with PyTorch is ongoing. So it's not really clear which version they are trying to integrate in PyTorch, but it's ongoing. So it's a good point. And you have some links here if you want to have more information about that. I'm pretty sure that Sylvain will be glad to answer you if you have questions. So staying a bit in model training, the few new strategies were presented also at the GTC. The first one is to say that the era of brute force scaling is over. So you cannot say, okay, I can train a model with the full internet in it because everyone is doing that. It's not a point anymore. The point is to have here super BPE, for example, one strategy. So classically, if you have a sentence like, by the way, I have a file on the Milky Way, in BPE, you have particularly one token per word, because here the words are really small, so you have roughly one word per token and per punctuation also. And the idea of the super BPE is to make sure that the expression comes together in one token. So by the way becomes one token, I am becomes one token, Milky Way becomes one token, because it's logical to have one token here. And the way they train the model is to say, okay, let's start with BPE, the classic BPE. So you learn, it's a kind of, you learn by syllabic approach first. When you learn how to read, you start with the syllabic approach, and then you recognize word and expression, and you can be more efficient once you read. It's the same idea here. And the point here, once you train with BPE and then you continue the training with super BPE, they can reduce the length of the sequence of token from 27 to 33%. So it's quite a lot, in fact, for this approach. So of course it's ongoing, so they are continuing to try to improve this kind of stuff. There is another method called Socratic MCTS. So it's about meiotics. So the idea is to teach a model, but to teach it with a special teacher. So the teacher will not give the answer to the model, but question. And the idea is to be sure that the model should ask itself question and say, okay, do I answer the question right? Is it logical? Do I have other way to think about that, etc., etc. So the idea is to question and to be sure that everything is fine, as we do, in fact, once you want to do a scientist reasoning, you have to ask yourself question to be sure that is it logical, is it nice, is it relevant. Quite the same idea in the retro search, but not totally. So the idea is to say in the retro search to sometimes you ask a question to a model and straightforward it's answer you the wrong question, but really fast. It's bad. And sometimes you ask a question to a model, it will think for 2 minutes and will ask you about the answer. And sometimes a bad answer in Thai also, because you ask a question in English and the model goes crazy and it answers you in Thai because why not? So this is the problem of underthinking and overthinking. So the idea here is to make sure that the model has a way to explore the graph of possibilities. And once he found that the answer will not be right, to deconstruct all the reasoning and start another path and try other thing, as we could do in science. In fact, once you try your path, you have an idea, and the idea is bad because it's life, and then you have another idea, and this one is bad, and you have another idea, this one is not quite good, but not so bad, and you improve it, and you build on top of that. So the idea is basically that. The fourth one is about test time training. So the idea is to generate 1 minute video. So it's a really long video because it's about 1.5 million tokens to generate such a video. So they try to find some ways to avoid all the problem that comes with this idea. And they also question the fact that we are not supposed to update the weight during the testing, and they try to update the weight during the testing to see what's going on, to see if we can do stuff. The argument is to say, once you are in an exam, for example, you can learn stuff during your exam. It's possible. For me, it's a bit late, but normally, yes, you can learn stuff. So why not with the model? For the model, I thought testing was mainly to prevent the overlearning and the overfitting, but maybe there is other reasons why I'm not. It's not my job. I'm not really aware of that. So if you don't take what I say for real, just check. Maybe there is news about that, and I didn't get the information. And the last one is synthetic data generation. So the idea is to say good data is really rare. So it's a fossil fuel of model training. And they want to have a way to generate good quality data to train model with. It's a kind of the approach of DeepSeek, if you have had a look into that. So that's for the model training and new strategies, but we will still dive a bit inside model training, but with FP4. So I know this title sounds provocative, but believe me, we are going somewhere. So, little reminder on precision and on floating point. So, float 32, it's 8 bit of exponent and 23 bit of mantissa and 1 bit of sine. Float 16, 5 bit of exponent, 10 bit of mantissa. Float 8, a 5m2, a 4m3, depending what you want. Int 8, you can say there is no exponent but there is a mantissa. Or there is no mantissa but there is an exponent, depending on the convention that you use. But let's say I use this one. FP6, a 3m2, a 2m3. And FP4, a 2m1, so 2 bit of exponent, 1 bit of mantissa and 1 bit of sine. And everything is fine, and everyone was laughing at this stuff. And the last one is int 4, so 4 bit of mantissa in that case, if I want to be coherent with my int 8. In fact, it's not good or bad for now. The point is, how many binates do we need? So if we express the dynamic range in binates, for example, so 277 for float 32, 40 for float 16, etc., etc., etc. The point is not to have the number of binates, and the better, the bigger the better. It's just to say, okay, but how many do I need? After several studies, during a training, you need something between 10 and 20 binates per tensor to have a well-trained model. Otherwise, we will have some problem. So clearly here, float 32, float 16 is okay. Too much, no problem. Float 8 is quite okay, in fact, quite close to what you need. So not really a good problem. And then you have the others, and you say, okay, but why they are in the slide? And of course, you learn about float 6 and float 4, and they are used to train and for inference. So what's the point? The point is, of course, FP4 is not an NP4. FP4 is a bit more complex than a classic float 4. FP4 is based on a block format. So the idea is to have metadata, typically float 8, and then you have a block of data value in a lower precision, so float 6 or float 4, and to get the value you need to multiply the metadata with the block of the data value, and you will get your data back, the data you encoded inside the block. And you can do that for another one, and you get your result, and everything is fine. The problem with that is you cannot do that with the software. It's too expensive, so you have to do that with the hardware. You have to design a hardware to do that properly. So if we do a dot product per tensor, you have two tensors, you have a scaling factor per tensor, and you do your dot product and everything is fine. If we push a bit, we can say, okay, let's do the same, but with block. We do a per block scaling factor, and we have a lot of blocks, and you do the same dot product, which is a basic of a matrix multiply, so it should work. So this is the point of this approach, the first point of this approach. So for example, for FP16, you have one scaling factor per neural network, and one for FP8, you have one scaling factor per tensor, and for FP6 and FP4, you have one scaling factor per block. So that's the trick here. And the second generation of transformer engine is supposed to deal with this kind of stuff. But there is still a trick, because you have your distribution of value of your tensor value, so in the tensor value range. And then you want to put these values inside a 4M3 representable range, for example, so a float 8. And you want to push the distribution something like this, for example, so with a shift. So here with this shift, you can say, okay, if I drop a bit here, I keep precision. So if I fit from here to here, I lose precision. If I compute this distribution and distribution may drop here or here, it's okay. So you shift a bit your distribution here to maintain accuracy as much as possible for the computing. And the trick here is, how do we do the conversion? And for that, there is rounding. So you round from the tensor value range to the float 8, you round to the A4M3 range. So in that case, it's rounding to the infinite. It's a bit more trickier than this, but in that case, it's a simple case, it's rounding to the infinite. And in the other way, once you want to get back your value, you round from the A4M3 to the tensor range, and you run in the other way to fix the problem. As Vincent explained to you in the precision webinar, you have to be careful about the rounding, because you will have some problem with that. So here they take care about the rounding, because you have only one bit of mantissa. So by definition, if it's wrong, it's wrong. So you have to be careful about that. So the rounding matter in that case. So some results with FP4. So FP4 speed ups about 1.8x on the inference over FP8 at ISO settings, so it's quite okay. You can combine it with PTQ or Quads or other method to see. The accuracy may drop by a couple of percentage points, so it's not that much, 0.2, 0.3%. It's not really a problem. They tested that on DeepSeek, Llama, and Nemotron. Of course, much more, but I don't have the place to do everything. You can watch the presentation if you want to know more. For FP4 SVD Quant, it's also possible to generate image. So the images are really close, quite equivalent to BrainFloat 16. In quality, it's okay. There are some details, or of course, some details are not quite the same, but it's quite close. And there is also software support. So CUDA 12.8 with Cutlass, with Cublas, with cuDNN, with PyTransformers Engine, with NVIDIA Model Optimizer, with ONNX, with TensorRT and TensorRT LLM. So you can play with that if you want, no problem. So we will have to talk a bit about Tensor Core. No, I already talked about that during my presentation on GPU architecture, but let's remind a bit about Tensor Core. So Tensor Core is just here to do a matrix product. So here the yellow matrix with the blue matrix to get the green matrix. So if I bend this a bit, I get that. And to do a matrix product with this hardware, I do all the multiplication at the same time and then all the reduction. and boom, I have my matrix product done. So we have a lot of tensor core inside the GPU, so few of them, and here you have the full family, practically the full family, because the problem is Blackwell does not fit in my slide. I'll have to dezoom at some point. But here you can see you have FP16, you have FP60, 62, 64 TensorFloat, FP8, FP16, int8. You have BrainFloat also with the same size of FP16 here. And you have int. You have integer also for A100 and A100. You want to compute some integer, fast integer, matrix multiplication. So let's start gently with mixed precision simulation. So this team is presenting that for geostatistical and spatial simulation. So the idea is to simulate what's going on the Earth for geostatistics. And they use a Cholesky factorization. So the idea is to have a matrix and to decompose it into a left matrix, so a triangle inferior matrix, times its transposed. And they use a tile scheduling, we will see that in a moment. So the point of their approach is also to say, okay, let's try mixed precision, because they have a speed up of 15 or 15 or 16 depending on the architectures with V100, A100, and H100. So it's worth it to try to drop the precision they had with float 64 to float 16 with, of course, the same result, and to be sure that they master what they are doing and they know what they are doing. They play with that, of course. And they are portable, so they did a good job with backends and well-defined backends, and they can use the library of the vendors, or the blast library of the vendors. As we bother you since the very beginning of all this webinar, think about the backends. They will simplify your life for the rest of your development. If you want to change it, to change the backend, you can. If you want to use another hardware, you can. You don't sign with Aubert to a certain hardware. So it's they did that, and it's really good. And they were able to test that on several big computing centers, so Frontier, Summit, Alps, and Leonardo, for example. And so what's going on? So the Cholesky factorization, so they want to determine this matrix. And so they start with this kind of precision. So the idea is to have a triangle matrix with blocks. So each block here is not one value, it's a dense matrix. And then they move to this matrix, to a matrix with various precision inside it. So lots of precision near to the diagonal, less precision in the opposite, and single precision to have a nice transition between everything. So nice standard approach. And so they change that and they say, okay, but let's play with it and reduce as maximum as possible the precision of the computation and maintain the result of the computation. And they managed to do it with that. So here they changed a lot, and they had a lot of half precision and single precision inside the double precision to be sure that everything is fine. And they were able to do that, and it's really impressive. And they have a direct acyclic graph, so DAG, to schedule the tiles. So the idea is to start with the first one, and then you have a graph dependency between all the tiles here to process the tiles at the right order to improve all the realization of the computation. And they have some results. So here we have some results with 64, 138, and 256 nodes on Alps. So they did that on Alps. And in red you have the original implementation on float 64. And here in the weak correlation you can have, you see that even with 64 nodes with their method, they can beat the float 64 implementation here, because they know what they are doing and they check everything to be sure that everything is fine. And they can push further with 256 nodes here. So from 1.84 million values, so it's a really big matrix, in fact, to 3 million values here with their tricks, with their knowledge of this matrix. And the bigger the better, because in this kind of simulation, the more you have values and the more precise your cells inside the simulation are, because the smaller they are, so you can have simulate much precise phenomenon. So in medium correlation, we need also maybe a bit more of precision. So if we have only 64 nodes, it's not enough, of course. But with 128, you can beat they can beat the performance that they have before with the dense float 64 approach. And they can push further also with 2.46 million of matrix size, so it's a really big matrix here. So it's nice also to have that in mind. And of course, for strong correlation, you need much more precision. So float 64 are closer to the best one here, and here you, in 128 nodes, you cannot beat the dense float 64 here, but with the same number of nodes, you can push also further the computing. So 1.84 million here and 2.05 million here. So you can still push further 20%, 10% maybe, about 10% more here improvement. Quite okay to play with that. But it's not the end. For this team, yes, for now, but we'll move to another team. And for that, we have to talk about floating point computing. So floating point computing, so a brief reminder, as Vincent already explained that to you. A float 32 is -1 times power of the sign, and 1 plus the mantissa, because of course the mantissa starts with 0, so we have the first one is the first one is 3. And plus times 2 exponent minus 127 to have negative and positive exponent in float 32. So this is a convention. And let's do that, but with float 12, because I don't have enough space on my slide to do that with float 32. So let's say I want to perform an operation between A and B. Whatever the operation, no problem. To be sure that it's possible, B has to match the exponent of B has to match the exponent of A. And so we have to change the B to be sure that the exponent will be the same. So we push the exponent a bit and we move the mantissa as we increase the exponent to have the same number. And at this point, as Vincent said to you, you can drop some information and lose precision because your important value are away from your mantissa. Can happen. But at this point, you can perform your operation and everything is fine. And then you perform the operation, and once the operation is done, you have again to normalize the mantissa. So put the mantissa where it should be, so here, and having the good exponent here. If you don't have the normal or stuff like this, but classically you have to do that this way. So let's talk about float 32 emulation with bridge float 16. So let's start with multiplying polynomials. So we have two polynomials, a and b. So with small a factors and small b factors. And we have k, k0, k1, k2. You can see that as a coefficient of a polynomial. So x to the square, x are 1, for example, or the opposite, whatever. Once you multiply polynomials, you will have something like this. So of course, it looks like the matrix product, normal. And by doing that, we have a times b. So it's a tensor product between a and b. And k times k. which is also a tensor product between k and k. And to perform the reduction of that, you have to do a dot product, and then you have your result. And everything is okay. No problem. So let's try to do that with float 16. So we have 9 float 16 methods. So the idea of this method is to express one float 32 with 3 brain float 16. So with 2 power of 0, 2 power of minus 8, and 2 power of minus 16. And see what's going on. So as before, we have a times b, so which is a tensor product. We have k times k, but here we know k already, so it's this one. So we know that we have value from 2 power 0 to minus 32, so a wide range of magnitude. And to get the result, we do a dot product of the two. And here you have to think about Vincent again, because it's about precision every time. Here you know that the matrix is not well conditioned, so you want to do an ascending sum to keep as much precision as possible, as Vincent showed you in the webinar of the precision, computing precision, in the one of the first webinar we had in the school. So this is the trick. But of course, we don't want to use all this trick just to multiply two numbers together. Of course, it's not enough. We want to do matrix multiplication. So general matrix multiply emulation of float 32. What's going on? Here, I start with A and B and float 32. So 4 by 4 matrices. Let's start simple. Then I have my matrix of K, so the matrix you already know, to convert all the values of float 32 to brain float. Then we do some slicing, so we compute the brain float 16 matrix with the CUDA cores inside the GPU, so with K and with A, to have the A matrix version of brain float 16. We do the same with CUDA cores for brain float 16 for matrix B. Then we perform the multiplication of these two matrices with the tensor cores. And of course, you remember that brain float 16 with A100 and H100 are really, really big. So you need to have big matrices to multiply to be efficient. And you have big matrices with this method, so it's nice. It's really good. It's a really good point. And then you do unslicing, so you do the sum I showed you before, with CUDA cores also, and then you get back your result with float 32, and you're happy. And it's really fast, because the matrix multiplication, so the thing which is costly, is made by a big tensor cores tuned for this precision, for this low precision computation, and it's really fast. And in terms of simulation, so it's another team with the weather simulation. So they use this library, this trick of NVIDIA for that. And on GB200, they did some simulation. So with 25 kilometer resolution for the weather simulation, or 2.5 kilometer resolution. And it's sometimes you have a 2.4 speed up compared to the classical way in float 32, and sometimes you have a better precision. Here you have the error and the resolution, and you want to be close to 0. And here you see the distribution is much more peaked, and it's more peaked because you have less dispersion in it. The precision is better. It's a really good point. So quite really a good point for that. But of course, it's not the end. Because you see me come, if we do that for float 32, why not for a bit more? So let's emulate float 64. So float 64 is a bit different. It's a linear combination of 5 to 9 int 8. So it's with integer and not with other kind of float. So float64 is a 52-bit mantissa, so just to remind you. And if we want to do that with matrix A and B, as I did before with the float32, we have 56-bit mantissa. So for example, with k s equals 7. So let's pick 7 int 8 to encode the one float64, for example. Is the average of the 5 to 9. So let's have a look how it's done. So here with slicing, I get my int8 matrix with CUDA cores, so much bigger matrix than before, of course, because we have 7 by 7 matrix increasing, so 49 more data and not a factor 9, so much more information. We do the same, slicing int8 with CUDA cores for the second matrix, so B. Then we use the tensor cores to do the computation, and you have to remember also, we have lots of computation possible inside A100 or H100 in 8, so at last we can use them now with this trick. And then you do the end slicing with this big K matrix, and you get back with the tensor core, you get back the result on float64. The really interesting part here is you can use the combination you want. If you want 5 int 8, you can. If you want 6 or 7 or 8 or 9 or whatever, you can. You are not stuck and say, okay, I want to emulate float64, but I have to use float32 or float16 or something really strict. You can say, okay, I want this amount of int 8. Let's see what's going on. And you get this nice stuff. So let's talk about results. So it's about material science, it's with Berkeley, and they have this kind of result. So here you have, in 52 bits of mantissa, you have the float64 here. And here we have the difference here. So here you have the size of the dimension of the matrix. So from 1024 to 32768 here. And you have the reference, so in float64 here, and you have the speed up over the float64. So float64 is 1, is the reference, and you have the speed up with what you want to do. And for most applications, so you can use 9 on 8 or 7 int 8 to simulate, to emulate a float64, and you will be here. So from 1 point something, 2x, 3x, something like that. And then if you can lower your precision, because you can have 3.56 something, you can have something close to speed up of 5 at some point, which is quite interesting also. So that's for the floating point part. So about accuracy, so float64 accuracy. So here you have the float64 in black dot. You have the triangle with 64 bits, so S equal 8. So here they are practically overlapping each other. So it's a QR factorization. So for to have a look and to see what we can do with this method. And the point is to play a bit with the factorization and to say, okay, let's try with 6 int 8 or 7 or 8 and see what's going on. So with 500 matrices, they did the study at NVIDIA. Now, so you see it's quite okay. If you say, okay, I want this precision, so 10 to the minus 15, you can use the number of int you want to emulate your float64, and you can play with it to have the best the result, the precision you want, and to keep the better performances you want. And they had an automatic version to choose automatically the precision you want. and you can get this, the blue dots here, very consistent, in fact, here, to pick the right precision compared to what you want. So here it's really good compared to the expected precision here. You have a much better precision here. So it's working. So to finish on floating point emulation, current algorithm fall back on float 64, so classic double general matrix multiply if the emulation is not possible. Could happen sometimes. It's not well conditioned, or you have range values or stuff like that. Some libraries will have the emulation soon. So QBLAS will be the first one, definitely. It's on the road, and then QSolver and QTensor also to have that. They will have interfaces to check to tweak the control of the emulation of the algorithm. So we'll have to tell which precision you want, stuff like this. It would be nice. And tools for profiling the precision are in development for now for the emulation. So it's not ready yet, but of course it's for the coming years. It will arrive quite soon. We will have at some point some tools for that. Really powerful stuff. So let's talk about math library now. So in math we have QSparse. So with a speed up from 1.45 to a speed up of 2.4 with the Blackwell architecture compared to H100. So he used much more tricks inside the Blackwell to be efficient. So they are up to date now. QFFT and QFFT MP, so fast Fourier transform for multi-GPU, multi-node library with as small overhead as possible. So they have a strong scaling on GB200 and NVL72 up to 64 GPUs. So it's roughly a speed up of 41x on 64 GPUs. So it's not perfect, of course, but it's quite good since. There is a lack of performance from 8 to 64 GPU due to InfiniBand, so it's a non-problem. But there is no problem on GB200 NVL72. It's fixed, so normally you should have a fixed problem if you run into that issue before. QDSS, so CUDA direct sparse solvers, now can use both CPU and GPU. NVComp, so the compression engine of NVIDIA, can decompress up to 600 GB per second with the Blackwell hardware decompression engine, so it's capable to use it now. So it's a 9x on Deflate and 4.5x on Snappy. You want to have a look also. And the last is NVJPEG. So now it uses the hardware decompression since Hopper and Blackwell to speed up decompression of JPEG. So can you also use it? Now if you have a up-to-date version, you can have some speed up if you are stuck with that. So inside an NVTX, so inside we have some news, because Insight now is already capable to profile CPU and GPU, but now it's also profiling the network, the storage, including the Linux virtual file system, so it's really good point. And then for NVTX, so you have this kind of panel here. So it's available in CUDA libraries, in C++ and Python mainly, not for all, but for a lot of them. And to give you a little example, with C++, you can have markers, you can have push-pop range, or you can have stat and range to add some information in your track and to be able to pick, okay, I was doing this kind of stuff inside my NVTX panel, inside Insight. You have a clear look of what's going on. You can do the same for Fortran here. So with a start and range here, I don't have the information for the other way to do it if there is one, but this one is really fine, so you can do it if you want. And as I said before, you can do that also for Python and Rust, and C++ and Fortran as well, as we did that already. A good point for Insight. Now it's time to talk about the future. So Blackwell Ultra NVL72, so a new version, still with Grace, so 72 cores. Blackwell Ultra, so 2 reticle size GPU, so 2 dies, as I said before in my presentation for Blackwell. 15 petaflop of dense FP4, now you know what FP4 means. 288 GB of memory, and here you have the rack, and second half 2025, 1.1 exaflop of dense FP4 inference, 0.36 exaflop of float 8 training, so 1.5 what's existing right now, and then new attention extraction, 40 TB of fast memory, and 14 TB per second of CX8, so network communication in the rack. Next, Vera Rubin NVL72, so Vera CPU, so new CPU, the next of Grace, so 88 custom ARM cores, so it was 72 for Grace, here it's 88, 176 threads, 1.8 TB per second of NVLink chip-to-chip. Then Rubin GPU, so 2 reticle size GPU, so 2 dies, as I mentioned for Blackwell. 50 petaflop of float 4, 288 GB of HBM4. This is the rack. Second half of 2026, 3.6 exaflop of dense FP4 inference, 1.2 exaflop of float 8 training, so it's 3 times the capacity of the one just before, the one of the slide just before, so the Blackwell Ultra rack. 13 TB per second of HBM4, 75 TB of fast memory, 260 TB per second on NVLink 6, and 20.8 TB per second of CX9. And the last one is Rubin Ultra NVL 576. So it's still a Vera GPU, 88 custom ARM cores, etc. Then we boost a bit Rubin with Rubin Ultra, so it's 4 reticle size GPU, so 4 dies inside one chip, 100 petaflop of float 4, 1 TB of memory, which is insane, let's be honest. The rack here, and so for second half 2027, 15 exaflop of float 4 inference, 5 exaflop of float 8 training, 14 times the Blackwell Ultra rack, 4.6 petabyte per second of bandwidth, 365 terabyte of fast memory, 1.5 petabyte per second of NVLink 7, and 115 terabyte per second of CX9, so the network inside Rubin. And speaking of the network, as I said before with the nickel slide, sometimes you want to have a really fast network. So classically, you have your rack here, you have copper to do all the communication inside the rack, and optic fiber to do communication between racks and between all the alley you can have, the corridor you can have inside your data center, or your computing center in that case. If you need to have a really efficient communication, you might want to switch from this to this with practically all optic fiber everywhere for all the GPU to be able to make sure that all GPU can talk with all GPU really fast. So, of course, it's quite difficult to put that together, but you might wonder that. In real time, in real life, it's something like this. The classic computing center, you have this kind of way with a lot of stuff in it, of course. So copper for the inside communication inside the rack, and optic fiber, so you can barely see it. Here you have the blue here, and you have the blue here also, so to communicate between the rack. But if you want to solve a problem which involves a lot of communication, not only for models, but maybe for simulation also, whatever, why not? You have maybe to use this kind of architecture. So they call that AI factory because they want to sell them to people who are doing AI, but you can also need them if you want to, if you have a lot of communication in your computation. And this is mostly optic fiber. So optic fiber inside the rack, outside the rack, you have 3 ways of optic fiber inside your computing center. Everywhere you have optic fiber everywhere. But of course there is a problem because of the transceiver. One transceiver is about 30 watts, which is a lot. And in this kind of design, you can need almost 6 transceivers per GPU. So you have one GPU, which is quite 240, 300 watts. And behind it, you have a 180 watts or 200 watts mostly of something which is not computing anything but just converting optic signal to electronic signal and vice versa. And that's it. It's quite annoying. And the point is, once you want to build a data center like this or a computing center like this, you can have an issue because the consumption of the transceiver can be 10% the consumption of the whole data center, which is a lot. So how to fix that? It's silicon photonics. So the classic way of doing that is to have a transceiver, so like this. So you have the input of optic fiber here, 1.6 terabit per second, for example. You have an externally modulated laser, you get the DSP, you get to the port cage, and you get to PCB, to substrate, and that you have the ASIC, you get your electron, and you're happy. Everything is fine. But the problem is, as I said before, it's 30 watts. So you have 10 watts for modulated laser and 20 watts of DSP. So it costs a lot. And moreover, you will have a lot of signal lost. You need 8 lasers for 1.6 terabit per second, and you lost 22 dBs, so 22 decibel. Each time you change materials here, you will lose some signal. That's a pity. That's quite problematic. So they change, at NVIDIA, they changed the design, and they came with that. They came up with that. So the point is to have one laser in here, and then we have a silicon photonic here. So the idea is to put basically the transceiver inside the switch and not outside, in fact. And then you have the substrate and the PCB and a contiguous wave laser. And inside the silicon photonic, they have micro lenses and micro mirrors, and they will move them really fast just to light or turn off the light really quickly without having to turn off the laser, of course, because it's not a good idea. And by doing that, it's only 9 watts, so 17 watts for the silicon photonic and 2 watts for the wave laser. And you need also only 2 lasers for 1.6 terabit per second transmission, which is quite good. And they lost only 4 dBs. So it's 63 times better than the one before, because of course decibel is a logarithmic scale, so it's way better than this one. So this saves a lot of consumption inside the computing center, and you can just consume less, or you can change at ISO consumption. You can say, okay, let's drop the extra consuming Maxender way, so this one, and use this one, and all the power that we gain, we can reuse it for computing, for example, which is quite a good point in a computing center. So they put that in Spectrum X, so Spectrum X SuperNIC or Spectrum X Ethernet switch, depending on what you want. So you have Spectrum 4, they switch 51 terabit per second throughput. You have also Bluefit 3, so SuperNIC up to 400 gigabit Ethernet row C sub 75 watt power envelope, so the full envelope, the full envelope consumption of the blade, if you of the engine. Then we have other spectrum X here, so photonics and quantum photonics. So we will not get to all the details here, but basically second half of 2025 and second half of 2026 we will have new news about them. So 512 pores, 128, 144 pores, with a lot of stuff. You can find what suits you here. And then NVIDIA Photonics, so inside the Spectrum X you have this kind of devices. So second half 2025 and second half 2026 with large computing center, so you need optic fiber connection. So you have, of course, 2 transceiver per cable, and we move from 2 times 30 watt to 2 times 9 watt per cable to be more efficient in that way. And here's a full roadmap. So coming from 2025 to 2028. So with Blackwell, so you already know Blackwell, Blackwell Ultra, Rubin, Rubin Ultra, and Feynman, the new one we will have in 2028. And Vera here, you have CX8, CX9, and CX10 here, Spectrum 7, Spectrum 6, Spectrum 5, and here we have Spectrum 4. The NV switch, normally you should have quite everything. So the liquid cooled, the 2 liquid cooled, so Kyber, the new one with Rubin Ultra, and Aubert, the old one with Rubin and with Blackwell. The old one, not so old, but common. And I will finish that with CUDA and beyond. So the new stuff which will come in CUDA at some point, but not yet. So first we have Cutlass with a Python backend and to get almost the performance of the C++. So it's possible to program tensor core in Python with Cutlass 4.0. So that's why my question to which Cutlass is involved inside, included inside PyTorch. If it's this one, it will be really efficient. If it's not this one, maybe we will have to wait a bit. NVMath Python, so it's an optimized math for GPU and just-in-time compilation. CuPy so Alice presented that already to you last week, but now I'm talking about the final product, because now it's still in development. So the point is to have a one-to-one feature NumPy GPU porting. So for everything, so you just import CuPy as NP and everything is fine, everything is scalable, and you can scale from with a full computing center without doing anything. That's the point, that's the goal of CuPy. Qtiles, I will present that just after that. So CUDA kernel, to express CUDA kernel in a simple way, in a simpler way. And tile IR, so I mentioned before, so it's about tile kernel with at runtime and ahead of time, so you can tile an intermediate representation on the fly to do stuff with it. And they both want to scale from a single CPU GPU to a full computing center, so quite a good approach. Then, speaking of parallelism, we have CUDA DTX, so CUDA distributed execution, so to master everything, to schedule everything. Then Nsight will be distributed into containers, and so you do not have to have a special container to run Nsight. Inside your sources, inside your project or stuff like this, you can have a container dedicated to that next to it, and everything will be fine. And so the last part is about Qtile. So Qtile will be available soon for Python and a bit later for C++. And the idea of Qtile is to say, okay, I have data to compute. Maybe they are structured, maybe not, but normally they are supposed to be structured a bit. And to do that, I will split my data into blocks and into tiles. And here we have a lot of blocks and one tile per block. And the point is to say that one tile is about one streaming preprocessor. So it's really easy to use, but you still have to have in mind that, okay, do I have enough computation from my streaming processor of my GPU? At some point, we will certainly have something on top of it to manage that for us. But if you have to split your data yourself, you have to think about that again. But that's the price to pay to have performances. And the point is about this design is everything, all the collective operations are over tiles. So the tiles matter. Don't use elements or stuff like that, only the tiles. And this is really efficient for that. So you can have you can split your data as you want. So with 4 tiles per block, with 1 tile per block, you can really play with that as you want. No problem. You play nicely with it. And the point is, it scales, of course, from single CPU to GPU to a full computing center. And you don't have to worry about that. Everything will be handled under the hood for you. You have to be bothered with that. And the last point is, of course, this is compatible with CUDA graphs. So you can use CUDA graph inside tile. So for now, obviously, because it's not ready yet, but this is a goal, to have something fully compatible with the CUDA stack, with CUDA graph, in a really simple way to express kernel, because of course, as we say that every time, particularly on all the webinar, you have to split your data properly to compute them efficiently. You cannot do that randomly, it will not be efficient. So thank you for your attention. Here there is a link to a big summary, all the notes I took from all the presentation I saw in the GTC. So it was about 41 presentations, something like this. So a lot of notes, a lot of slides, a lot of information. So if you want to have a look, and to have a look also at all the stuff I did not present to you because I don't have time to present everything. For example, stuff on rendering, stuff for pipelines, stuff for Rust computing, data format, stuff like this. I did not have time to present everything, so you can have a look to that. And thanks for your attention. If you have some questions, I will be happy to answer them. So here you will have these pages, and here you have all the notes I took from all the presentation I watched from all the GTC. So it was about 41 presentations, something like this. So you have all the notes, all the stuff. So I read for that. So you have everything. You have hardware, computing, simulation, AI, quantum computing, video compression, normalization, everything. Normally you should have you should have your information if you want. So thank you for your attention. And if you have some question, maybe we can have a bit of time to answer them. From Tom, I have a question regarding the summer school for those who will be in Nancy. I saw on the website that the container for different courses are available. Do we have to download and install them before coming to school, or we'll have a dedicated session for that in the beginning of the school? Yeah, you have to download them before the school because, of course, we will be something like 40, something like that. So you don't want to download everything at the same time, so try to download them. Maybe next week should be okay, but before the school it will be better. And we have to download before the school. Yeah, which one do I have to install? Between the 3 different containers. Oh yeah, once you have 3 different containers, you have a light container. The light container normally is for computing centers, so you can start jobs with them. And then we have code server container. So you can jump inside your image on your laptop with your favorite browser, so you don't have to worry about that. And the last one is for Kubernetes, so also for computing center when they run Kubernetes. So normally, if you prefer the light one, you can check the light one because it's much smaller, of course. If you prefer to have a VS Code and to play with it, you can use the code server version, really depending on what you want to do. Normally should be okay. Everything is explained. Normally, if I have too much tab. If I go here, here, oh yeah, inside the site. So here you get the list of the satellite sites, you get the list of all the containers here. So maybe we will have some update next week, possible. It's possible to have that, but normally everything should be quite okay. So you have all the containers, and here you have some explanation. So how to use a container of code server, how to use them on a remote server, because maybe you don't have a big laptop, but you want to jump on your server, maybe. So I explain also how to do that, how to submit a job. So with htconda, because here in ANSI we have htconda. If you have Slurm, we also have some stuff here, but there is a Maisonnet documentation if you want to have a look. And you have the script also inside the container, how to do that. So you have everything here. So don't hesitate to jump on this documentation to have a look and to check if everything is fine. If you want to do a bare metal installation, it's also possible. Maybe it's a bit too much, but depending on what you want to do, it could be okay. So don't hesitate to play with that and tell me if something is not clear. I will fix it. Okay, so thank you everyone for being here, for attending this webinar. So we will see you next week with the last webinar of the Grace Code series. So it will be on how to convert your CUDA kernel inside the Sycl kernel. So with an automatic way, with a lot of tricks. So Joel will present that to you next week. And the week after is the school. So register, as Mary said, register if you don't want to miss the school, and that's it. So have a good day and bye.